All right, welcome to AP Chemistry. This is Unit 1, Lesson 1. And in Unit 1, we're mostly going to be reviewing things that we learned in Baby Chem last year or the year before. So this first lesson is focused on measurements and Sig Figs, which we spent a lot of time on last year. So we're going to start with measurements, just kind of reviewing some of the units that we use and the idea of certainty in our measurements, like precision and accuracy, how many decimal places we should use, things like that. All right, so with measurements, typically in chemistry, we are talking about measurements that have a number and a unit. If we just have a number, it is meaningless without a unit. If I say 5.2, that doesn't mean anything. If I say 5.2 grams, now we can understand what that means. This is called a quantitative measurement or a quantitative observation when we measure something that has a number and a unit. We also can make qualitative observations, and we do this often in chemistry as well. So things like color, texture, odor, things that we can describe, but we can't measure them with a number and a unit. Quantitative measurements are really important in chemistry because they allow us to compare our results to either a known value or what someone else got. If we're taking the temperature of an object, we can see if we all get the same temperature rather than using a qualitative measurement where we would, maybe some of us would describe it as hot and some of us would describe it as just warm. So those types of qualitative observations tend to be more subjective, whereas quantitative are a little bit more objective. Typically in chemistry, we're going to be using the SI units. Most of these are based on the metric system, but not all of them. So for example, the SI unit for mass is the kilogram. The SI unit for distance is meters. One of the weird ones that we talk about is temperature. So in the metric system, remember the temperature unit is Celsius, but in the SI system, the standard unit is Kelvin. And we'll be discussing in this first unit here, not today, but in I think the next lesson, how to get from Celsius to Kelvin so you guys can practice that again. All right, so typically with our metric units, our SI units, we can use prefixes. And these prefixes allow us to change the size of the unit so that it makes more sense to whatever we're measuring. For example, the SI unit for length is meters. But if we're measuring something really small, like the size of an atom, using meters is not going to be very helpful to us. It's going to cause us to have a lot of, our number will be in scientific notation for sure. So we can use other numbers like nanometers or picometers, putting that prefix in front of our base unit, our standard unit, changes the size of it. So what this chart says is that 1 nanometer is equal to 10 to the negative 9th meters. Similarly, 1 kilometer is equal to 1,000 or 10 to the 3rd meters. So the ones that are most important in chemistry are kilo, centa, milli, micro, nano, and pico. The rest may be used from time to time, but the ones you really should know are those 6. So The other way that we can change a unit other than adding a prefix to it is by combining two or more of our SI units or base units. So we can take some of our metric units and combine them to make things like volume or density. So volume is one that we use a lot, right, in chemistry. Volume comes from the fact that if we want to measure the volume of like a block or something, a rectangular prism, we would do length times width times height. So for volume, we wind up with basically centimeters times centimeters times centimeters, and that gives us centimeters cubed. We can also use things like meters times meters times meters and get meters cubed. But in the stuff that we'll be using in chemistry, we'll have small enough quantities most of the time that centimeters cubed is more useful to us. Another thing that is important to note is that 1 centimeter cubed is the same as 1 milliliter. That's basically the definition of a milliliter is a centimeter cubed, that length times width times height. Typically we use milliliters or liters when we're discussing the volume of a liquid, and the centimeters cubed is more for the volume of a solid, like a rectangular prism. But we can use centimeters cubed when discussing a liquid as well. Density, as we know, is mass over volume. So to combine those units, we take the unit for mass, which is grams, over the unit for volume, which we just found was centimeters cubed. So the unit for density, because it's found by dividing mass over volume, is grams over centimeters cubed, or grams over milliliters. One important distinction to remember is when we're discussing mass is the difference between mass and weight. Last year we said that mass is the amount of matter in an object. We can also say that it is the resistance of an object to changing its motion. So how much it resists movement. Mass is always constant. So that amount of matter in an object, the amount that it resists motion, is going to be the same no matter where that object is. But weight is how that mass responds to gravity. And so on Earth, the gravity doesn't change enough from one location to another to cause a difference in weight. But this does become important, if you go work for SpaceX someday or NASA and you're sending things to the moon or to Mars, mass will be the same. Mass of the things you're sending would be the same here and on Mars, but the weight will be different. All right, so one thing that we spent a lot of time talking about last year is how to record a proper measurement. And so when we're looking at our measuring device, we need to look at the smallest tick mark, and then we need to record one estimated digit past that tick mark. So for example, if our smallest tick mark is in the ones place, then our estimated digit would be in the tenths place. So this example is looking at that. So a chemist is analyzing a sample of polluted water. They measured out a 25.00 milliliter water sample with a pipette. At another point, they used a graduated cylinder and measured 25 milliliters of a solution. The question here is there a difference between these two measurements, 25.00 milliliters and 25 milliliters? So while the numbers 25 milliliters and 25.00 milliliters may seem equal, they actually mean very different things. So when we look at 25 milliliters from that graduated cylinder measurement, what that is telling us is that the graduated cylinder had its smallest tick marks in the tens place. And the scientist had to estimate this ones place, this 5. And so the volume of that that measurement could be anywhere between 20 and 30. That scientist had to make an estimation of that 5. However, when we look at the one from the pipette, the 25.00 milliliters, that means that our smallest tick mark was this 10th place, this 0 in the 10th place. And so the scientist is estimating the 100th place in this situation. And so this measurement has much less uncertainty because we know that it's somewhere between 24.9 and 25.1, most likely between 24.95 and 25.05 if we're looking at the tick marks. And so that is much more precise than this 25 milliliters, which could be anywhere between 20 and 30. And so this is going to be important this year as we do a lot of labs where you'll have to make a decision of what type of measuring device to use. And depending on the lab, sometimes we want something that is really precise so that we can get really clear measurements. And in that case, you'd want to use a pipette. In other labs where we're trying to do something more qualitative or the efficiency is more important, then using something that is less precise can actually be more important. And we'll discuss that as we go through and do some labs this year. So this kind of leads to uncertainty in measurements, right? Because we're talking about the number of digits that we should have in our measurement based on the device that we're using. So remember, there are 2 ways that we look at the uncertainty in our measurements. There is precision and accuracy. Precision is when our measurements are all close to each other. So if we all measured the same object, we would all get very similar results if we were being precise. Accuracy is how close we are to our actual value, to what it should be. So we can have measurements that have low accuracy and low precision where they're just kind of scattered. They're not near the true value. They're not near each other. That happens when we're not paying attention, when we're not using the correct measuring devices, things like that. We can also have measurements that are not accurate but are very precise. And that happens when our measuring device there's something wrong with it. And so every time we make the measurement, we get the same answer or a similar answer, but it's never correct. It's never what it should be. So that can come from faulty equipment, or just the fact that none of the equipment that we use in a lab is ever going to be perfect. In this bullseye example, you can have high accuracy and low precision, but in a measurement, this would actually be impossible because we can't be close to the true value, but far away from each other. It just wouldn't be possible. And then high accuracy and high precision is obviously what we want most of the time. We want to be close to the bullseye, close to the actual value, but also close to each other, have our measurements all be very similar. All right, in this second example, we are looking at a student who is trying to check for the accuracy of a graduated cylinder. So the way they did this was they took a burette, which is a much more precise measuring device, and they emptied the burette into a graduated cylinder. Each time they measured the liquid to 25 milliliters in the graduated cylinder. So each of those is the same. But remember, when we say 25 in a graduated cylinder like this, we're saying that the 2 is certain, but the 5 is not. Then they measured the burette volume, how much they had let out of the burette into the graduated cylinder to fill it to that 25 milliliter mark. And so we can see here that each time the burette volume was about 26.5 milliliters. So the question is the graduated cylinder accurate? So we see a lot of good precision in this set of measurements because the burette measurements were all very similar. So each time we measured into the graduated cylinder, we were putting about the same amount of water. But the average value from the burette is greater than 25 milliliters, which is what was being measured on the graduated cylinder. It's greater than by about 1.5 milliliters. And so the graduated cylinder is not very accurate. So this is an example of systematic error. This happens when there's trouble with the equipment. So the same error occurs the same way every time. In this case, the amount of liquid is a little too high every time. And that is because of the equipment, not because of the person using it. So the other type of error we can have is random error, which is typically due to user error. So that would be evident if we saw that the difference was sometimes too high, sometimes too low, sometimes spot on. If it's different every time, that is a random error. Random errors can be fixed by practicing, paying more attention, being more careful with our measurements. Whereas systematic errors, we can't fix that unless we get new equipment or better, more precise equipment. All right, so all of this finally leads into sig figs, significant figures. I have this linked in Canvas, the handout that tells you the Sig Fig rules, but just a quick review here. Remember that all non-zero numbers always count. If there are zeros that are trailing, and there's no decimal place in the number, then those zeros will not count. If there's zeros that are leading, and it doesn't matter if there's a decimal place or not, leading zeros will never count. When we have a decimal place in the number, those trailing zeros wind up counting, but the leading zeros would still not count. A sandwiched zero will always count. So zeros that are in between two non-zero numbers will always count for sig figs. So for example, this first one has 2 sig figs because these trailing zeros do not count. This last one has 4 sig figs because these sandwiched zeros do count. In this example, we're asked to find how many sig figs are in each number. So we remember our Sig Fig rules. So first of all, leading zeros never count. Trailing zeros only count if there is a decimal in the number. And trapped or sandwiched zeros always count. So this first example, we have 2 leading zeros. Those will not count. We have 1 sandwiched zero here. And then the other 2 are non-zero numbers, which always count. So these 3 digits will be our 3 sig figs. In this second example, we again have 2 leading zeros, and so those will not count. We have 2 trapped zeros here and 1 trailing zero. We know that the trapped zeros will count along with these non-zero numbers. The question is this trailing zero, and because there's a decimal place somewhere in this number, this zero will count. So we wind up with 1, 2, 3, 4, 5 sig figs. In this question, we have a trapped zero between these 2 numbers and a trailing zero. However, there is no decimal place anywhere in this number, and so this trailing 0 will not count this time. We wind up with 3 sig figs. Lastly, we can also look at numbers in scientific notation. However, it's important that you do not take it out of scientific notation to count the sig figs. Leave it the way it is, and just look at the number prior to the multiplication sign. So you can ignore this times 10 to the 6th when you're counting sig figs. So we have a trapped 0 and we have a trailing 0. Since there's a decimal place in the number, this trailing 0 will count. We wind up with 4 sig figs. In this example, we are using our multiplication and division rules for sig figs. So the first step for any sig fig problem is to just do the problem as normal. So you just do the multiplication or division as normal. So for this first one, I'm just going to punch it into my calculator, 1.05 times 6.135. And I'm going to write out the whole answer that I got, which was 6.44175. Now I look at my original problem, and I determine the number of sig figs in each of those numbers. So this first one has 3 sig figs because it's a trapped 0. This one has 4 because there's no zeros. And so I choose the one with the least, and that is how many sig figs my answer must have. So we would have 1, 2, 3 sig figs. This number after my last sig fig is a 1, so it does not round up. So my final answer would be 6.44. I can do the same thing with division. So I would do 5.200 divided by 0.12. Write out my answer, 43.333, blah, blah, blah. Again, I come back here and I count my sig figs. This one has trailing zeros, but there is a decimal, so they will count, so there's 4. This one has a leading 0, doesn't count, so there's only 2. The least amount is 2, so my answer will need to round to 2 digits, 2 sig figs. So 1, 2. Again, we have a 3 after that, it's less than 5, so it's not going to round up, it's going to stay as 43. Lastly, we can combine multiplication and division into the same problem because they have the same rules. So I can do 2.560 times 275.1 divided by 8.8. And I can do that all in one step because the rules for multiplication and division do not change. So I'll write out my answer. Then I do the same thing. I count my sig figs. 1, 2, 3, 4, 2, 3, 4, 2. My least amount here is 2, and so I need to round my answer to 2 sig figs. So I would have 8 and 0. Now this one's a little tricky because if I just write 80, now my answer only has 1 sig fig, right? Because trailing zeros only count if there's a decimal. I can solve that 2 different ways. I can put a decimal after the 0 and call it good, or I can write that in scientific notation. Either way is perfectly acceptable. In this example, we are using the Sig Fig rule for addition and subtraction. Now this rule is different than multiplication and division, so you have to be careful when switching between the types of problems. So for multiplication and division, we rounded to the number, or the least number of sig figs in our answer. With addition and subtraction, we are rounding to the least number of decimal places. So we start out the same, we just calculate the answer to our question. So this first one is 21 minus 13.8, and I get 7.2. Now I look at my problem. So 21 has no decimal places. 13.8 has 1 decimal place. So the least number of decimal places is 0. So I want my answer to have 0 decimal places. So I'm going to round that to 7. Let's do this next example. So same thing, 16.02 plus 33.156. Write out my whole answer, 49.176. Then I look at my original problem. In 16.02, there are 2 decimal places. In 33.156, there are 3 decimal places. My least amount of decimal places is 2, and so I want to round my answer to have 2 decimal places. However, the number after the number I'm cutting off is greater than 5, and so that's going to cause this to round up. So I'm going to wind up with 49.18 as my answer here. In this last one, we have a combination of subtraction and addition, but it does not matter because they have the same rule. And so we can just do this whole problem all at once, adding and subtracting at the same time. And we get 85.4598. Then I go ahead and look at my original numbers. In the first number, there's 1 decimal place. In the second one, there are 4 decimal places. And in the last one, there are 2. And so 1 is